In today's lesson, we're going to look at the key features of quadratic equations, expressions, and functions. We've talked about quadratics before briefly when we looked at different types of polynomials earlier in the year. So what is a quadratic expression? A quadratic expression is a polynomial that has a degree of 2. Some examples of polynomials could look like the following. We could have an expression like x squared, which is a monomial. We could have a monomial expression like 5x squared. A trinomial expression of x squared divided by 6 plus 3x minus 7 would also be a polynomial that's a quadratic. We could have less likely or less obvious examples. So for example, negative 2 times the quantity x minus 3 to the second power plus 7. If we were to simplify that out, we would end up with an x squared term, which would be a quadratic. And lastly, we could have something that's just a trinomial that we've seen before, 2x plus 7 minus 18x squared. Those are all examples of polynomials. Let's look at some non-examples now. So we're going to look at examples that are not a polynomial and the reason why they're not quadratic expressions. So the example of 1 divided by x plus 4 is not a polynomial because we can't divide by variables or have negative exponents. If we were to write this example out with a negative exponent, we would have something that looks like x to the negative first for the 1 divided by x part of the expression. Another example would be something along the lines of the square root of x plus 2 minus 7. So this is not a quadratic or a polynomial because there's a square root in the problem. Finally, the example that we'll use last is x to the third plus x squared. And in this example, it's not quadratic because the degree is 3. So what do the graphs of parabolas look like? We know what the graphs of linear equations look like. They're straight lines, right? They could be increasing, decreasing, vertical, horizontal. Quadratics are different. Quadratics create a U or N-shaped graph called a parabola. So we could have parabolas of varying different shapes. We could have parabolas that are narrow. We can have parabolas that are wide. We can also have parabolas that instead of opening upwards, open downwards. So those would be the N-shaped parabolas. So there's lots of different types of parabolas that we're going to be looking at over the coming days. We're now going to look at the key features in the graphs of quadratic functions and parabolas. So with the graph on the left, the first thing I'll point out is that our parabola crosses the x-intercept twice. These are our x-intercepts. In this case, the x-intercepts are going to be, well, the one on the right looks like it is at 2, 0. And the intercept on the left is at -6, 0. The graph also has a very low point. So this has several names, or it could be referred to as several different things. The first term you might hear is vertex. The other term you'll hear often is the minimum. And sometimes it could actually be called the turning point as well. So the vertex, aka minimum of this graph, the absolute lowest point is at -2, -16. Parabolas also have a line that runs through the vertex called the axis of symmetry. And this line that runs through it creates a reflection or a mirror image on each side of the parabola. Moving over to our graph on the right, we have another vertex. This time, the vertex is called a maximum because it's the peak of the parabola. And this vertex is at -5, 0. That's also our only x-intercept in this case. The line or axis of symmetry also runs through the middle of this graph. Our graphs can have other features. So the graph on the left has a y-intercept. This y-intercept is at 0, -12. And the graph on the right has a y-intercept of 0, -25. We can look at the behavior of the graph as well to either side of the parabola of the vertex. So looking at the graph on the left, starting at the vertex, when I look this way, the graph is increasing. That line increases. But if I come from the other side, if I come from the left side of the vertex, the graph is decreasing. So parabolas have two different types of behaviors. They have increasing and decreasing behaviors. Looking at the graph on the right, if I start to the left side of the vertex, our graph is increasing, and as it reaches the vertex, and this is why it's called a turning point, the graph then goes in the opposite direction, and now it's decreasing. So those are some behaviors that we need to look at as well. Finally, we'll look at the domain and range of the graphs. With the graph on the left, the domain, or x values, is all real numbers. We looked at something like this earlier in the year. The range of the graph, though, is not all real numbers, right? So the lowest point our graph reaches on the left is at -16. So that means all of the y values greater than -16 are part of our range. I could also describe the domain and range of the different behaviors. So if I wanted to describe the domain of the increasing part of the function on the left, well, the domain increases here, right? The increasing part of the graph is that part of the domain. So we would say, in that case, x is greater than or equal to -2. That would describe the domain of the increasing half of the parabola. We could do the same over on the graph on the right. Our domain here of the entire graph is all real numbers. But if I wanted the domain of the increasing part of the graph on this one, I'm looking at this section here, right? And that would be all of the x values to the left of -6. So we would say x is less than or equal to -6. The range of the entire graph, well, we have a maximum of 0, so the range here would be y is less than or equal to 0. And those are the key features that we're looking at in today's lesson. If you have any questions or you'd like to redo the task when you're done because you're not happy with it, send me an email and I'll get back to you as soon as I can. Have a good day.